All right. I'm going to flip through these. I don't need to do this again. So this is where we landed. Like we're worried about the fact that the internet keeps forgetting things. That was problematic. So one solution is to just go and give all the browsers identifiers. By the way, your phones all have identifiers. This is how they work. It's on the screen. This is how cookies work, though. How many warning dialogues have you ever seen about your phone identifier? Like none ever, right? You see cookie warnings all the time. Cookies are actually less privacy problematic than that identifier on your phone. You see one and not the other because this is visible to lawyers. This is visible to all sorts of groups because it's client side. So cookies, usually when I'm doing lectures on privacy for public engagement with software engineers, I almost always pull up cookies because they're this weird, interesting tale. They are probably one of the best pieces of software I've ever seen for privacy that in terms of giving control to the user comparative to other solutions for the same problem. You have a lot of control with these. And they promote public discourse. I remember speaking to a student journalist who wanted to know about cookies, and I'm like, well, why are you talking to me about cookies, and why aren't you talking to me about the unique advertising identifier on your phone? And he pauses, he's like, there's an advertising identifier on my phone? And I'm like, yes, but you know about the cookies because they're visible. They're designed to be visible, I realize, for a more discerning crowd. But with a cookie, the client manages the tracking. That's one heck of a statement. You should be aware at this point that we don't like users managing things. They tend to break stuff. But it does mean the client can delete them. The client can modify them. The client can alter them. The client can take one away and then put it back. The client could copy it and put it on a different computer. I don't cover that. That's called Firesheep if you do want to look it up. You can opt out on a per-site basis. The only way to deal with the tracking number on your phone is to completely change it. And that was only after a huge amount of backlash that even exists as an option. But you have to do it globally. Cookies, you can decide per website if you do or do not want them. They've got some access control on them we'll talk about in a moment. And this allows for public discussion. So I actually really like cookies. And Android, iOS, both went the other option that don't have most of these properties. So I am a privacy researcher, and that is coming out in this lecture. Cookies are managed client-side. That means you can view all of your cookies. In fact, I think I made you already do this in an activity, didn't I? Yeah, OK. Old news. You guys can view the cookies. This makes it impossible to silently track someone. Everyone that is tracking you via cookies is on this list. Period. There is no one else. So what's important about cookies is that they are only sent to the page if the domain matches the one on the list. So if you look at your managing cookies site, you'll see a whole bunch of domains listed here. These cookies will only ever be sent to that domain. So your browser is doing access control. In this case, it is doing the mediation. Is the reference monitor when it comes to cookies. It will only send cookies to the site associated with the domain it's about to send them to. Let's walk through that very quickly. So we have a little gingerbread cookie icon to indicate when we're actually talking about cookies. So I'm making this up. But the browser first requests some cute dogs. Please give me the web page. We went through this example on Friday. And when it sends that request, it also sends the cookies. So it doesn't even have the page yet. It sends the cookies in request for the page. Now it does this so that the server can make adjustments. So if the server sees that you're already logged in because you have an appropriate session cookie, it will helpfully send you the logged in page as opposed to, say, the home page. So this allows the server to make an adjustment. The server sends something back, and it can also add a new cookie. So you send the server's cookies to the server also sends cookies back. However, as we learned before, pages are made up of lots of sources. This includes, in this case, I'm making fun of Instagram. So when we try to put one of that picture in, one of the dogs in this this example, it sends the cookies that are associated with Instagram, so Instagram's cookies down to Instagram, and Instagram sends back the image. So even though we're only requesting a JPEG file, we still send cookies. And then DoubleClick is a renowned tracking site that definitely tracks you. So this website's using some tracking. It sends the tracking ID as a cookie, and DoubleClick sends a blank 0 non-existent image back. It doesn't even have to necessarily do that. It sends the tracking ID back again as a way of resetting the cookie. So most cookies have a time to live. And so whenever a tracking site is contacted, it will usually update its time to live to make sure the cookie doesn't vanish at any point. OK, I know I have this very early, but this is a very nice question. So I kind of want to stop and do a think, pair, share with it here. Sorry, this was meant to be done in the other lecture, but we spent a bit longer than I expected. Why are session cookies safe to use for security? I haven't really talked about session cookies too deep, but a session cookie is identical to every other cookie, technically. There's some distinctions involving how long they live, but that's it. A session cookie and a normal cookie are identical. Their only distinction is in how long they live, and session cookies are designed to live for a very short time frame. Keeping in mind, a session cookie is used for continued authentication. Even banks use these things. Like you log in, and suddenly you just don't need to do a second factor authentication because there's a cookie in there. Cookies can be read by JavaScript. No login or other common authentication is needed to read cookies. Right? You don't log in order to send a session cookie, do you? Your browser just sends it. Cookies are all basically stored in the same place on the computer. You can go in and edit your own cookies if you would like. So why on earth is this safe for banks to use for security? Why is this OK that you haven't logged into Google in the last month? You haven't logged into Google because it's reading your session cookie. I'm making fun of Google. You pick Facebook if you want, or any other large organization. You haven't logged in the last month. Why is this safe for security? OK, 1 minute thinking to yourself. All right, I'm going to double down on this point. The other reason that this is all safe is because the browser is doing access control for you. So the browser is making absolutely sure that the only website that can read a cookie is the website that set it. This is an old example that is unfortunately broken. But here I have a basic website. Actually, no. In one of the extra activities, which is 100% optional, I have set a cookie. The code behind the page I'm showing you here is sitting on that activity if you care to look at it. But here I have this page running. All it's doing is it's doing a pop-up alert. It's asking me to enter a name. And once I enter the name, it just reads the cookie. So Cami here is the content of the cookie. It's just being read out by the page. So here I've set it on Vanier. If I go to camivanier.com, running the same code, but in this case, I have the cookie being set to a random number. So even though the cookie has the exact same name, because it's actually the same code that's being run on both of these pages, because the domain is different, the cookie content is different. Different websites, even though the cookie name is identical. A website or server can only set cookies for its own domain or a higher level domain. So for example, Vanier.com can read set cookies for Vanier. Images.vanier.com can read set cookies for images.vanier.com and Vanier.com. So it can read cookies one below it in subdomains. I did not dig into this enough to know if you can do this like 7 deep and how. But anyway, this is a bit browser specific though. This is how most of the main browsers function. This is up to the browser. The browser is doing the access control. But this is how it's typically handling. And browsers typically forbid setting cookies for top-level domains. So com and .uk and co.uk, for example, you can't set a cookie for those. Why does it look like that? Remember BIBA? Access control. We were talking about this BIBA model, and we were kind of really mentally struggling over why I might try to have a BIBA model of access. Cookies are kind of, broadly speaking, falling under this concept that you can read down, let's see, no, sorry. Must not read data at a lower integrity level. So Vanier.com is considered the higher integrity level. Images.vanier.com is lower integrity level. Why? Web hosting. Where's web hosting usually done? In subdomains. So this person running images may be a client of this group, of the higher level group. So they can read below them, but you don't want the higher level reading up.
It can only set one level up.
I think it's only one level. Past one level, I think we start having a lot of browser diversity, at which point I can't really answer. It can definitely set one level up, or at least they could last year. I'm sorry, browsers change their behavior on a regular basis. But last year when I did test this, I could only do one level up when I tried it.
So, say we have a domain called like dynamic photos dot images dot vanilla.com. So this domain can only set cookies
For images, not
images.
No,
but not
read. No, sorry, you're right. It is set. Set and read only for one and below. And even here, we're only looking at Vanier.com. So if there was another one up on top of here, I don't think it can read it, but now I'm getting a little more hesitant because browsers differ. So main browsers all do this, definitely. If you go one higher, it gets a bit more. Test it before you trust me on this fully. The main point, though, is that it can't say, if you have a web page on Vanier.com, it cannot read the cookies for uwaterloo.ca. Just does not work. All right. We learned last time that websites are built out of more than one source. So if I have loaded Vanier.com, and that's what's sitting in my URL bar, is it only Vanier.com cookies that are read during the construction of this page? No. Because this is done per connection. So site A is being loaded by the browser. Site B may be contacted to retrieve content. So B here might say grab an image. When the site B is contacted, all of B's cookies are sent. This results in this situation. You're looking at two iframes. This is the earlier example. Whoops, there. Those are both Vanier.coms. They both say hello Vanier, and this is camivanier.com, so it says hello user. I am reading two cookies on this site. And I can do that because these are two different connections. Session cookies, so these are two different cookies. On the left is a normal cookie, on the right is a session cookie. While they look identical, the only big difference is on the left, it says expired max age, and it lists a time. On the right, it just says session. Unfortunately, the definition of session cookies are very fuzzy. Sometimes you just don't set anything. Sometimes you write session. Sometimes you pick a short time frame. If you ever try to do research in this, it's a nightmare detecting what is and is not a session cookie. The only consistency is that they tend to be, quote, short. But in case you didn't know this, Firefox, so in theory, if you don't have any expiration, when you restart the browser, it deletes all the cookies that have no expiration at all. Except Firefox does not do that. It likes to keep them around for improved user experience. So this is not consistent necessarily. And session cookies, okay, we're not getting into law for a few more lectures, but when we hit law, session cookies are legally considered less privacy sensitive because of their short time frame, because they're usually only handled for a little bit. And this will make sense on a couple of the next slides. So cookie-based privacy attacks. We're starting to edge into privacy now. Tracking across sites. So I already did this. We already built this whole thing. But I want you to pay attention now to this number, 758. So we have just loaded cutedogs.com. It contacted all these sites, it set and grabbed cookies, and it did 758 for a tracking cookie off the DoubleClick server. All right, so this is Cute Dogs. What would happen if I did this with, say, my bank? And my bank is also using DoubleClick because everybody uses DoubleClick. So if I flip between these, I might get some different numbers, right? I might set a different user ID when I talk to my bank. My bank is still talking to a content network, so they're sending some information. And they're contacting DoubleClick. And DoubleClick has the exact same number. This is how web tracking is done. As I said, half a second, that number is a reference into a database. So every time you visit a site that has a link to DoubleClick, it grabs the number, and it knows what information is sent to it, and it updates the server. This is how web tracking is done via cookies. Also, you may notice that a lot of things have get strings. I haven't put one in here for DoubleClick, but it is quite possible and fairly common, actually, to include the information about the website I'm on in a get string that's set to DoubleClick. So DoubleClick would likely then know that maybe I like dogs and bank at my bank because they know that I have been doing both of those things. Yeah, I showed this before. We talked about web pages as kind of being this template and how that template can change as it is executed. So one of the tricks I can do is my bank, which has access to my user ID at the time it constructs the page, can go and put together a new page, which means it can rewrite all the URLs. One of the things it can do is it can dip it into its nice little server and convert my user ID number to the user ID number it's using for its content network or for something else. So my bank, it might say content equals this. So it's constructing that URL live. And there's nothing stopping it from putting whatever it feels like out of its server into that. So this is an example from the United States. So the United States decided they were going to do healthcare worldwide during the Obama administration. This was done partially by going and creating a web page that allows people to go and sign up for healthcare and search for different healthcare providers. This is a government-run web page. There's some interesting stuff in this URL, isn't there? So this is sending to DoubleClick. So this is a tracker, pure and simple. There is nothing else DoubleClick does other than track people. And if you look down through the URL, you'll notice that it's coming from, so it's a reference from healthcare.gov. So it's saying what web page the user's on. They're a 40-year-old smoker who's pregnant and lives at this zip code in Arizona with an income of $35,000, and they're on step 4 of the login process. This is a real example. So when we say tracking, we don't just mean that they know that you went to every single page. It is up to the page who constructs this. What developer worth their salt would have bothered spending all the time to set this up? No, none, right? Because this is horrifically underfunded, bluntly speaking. I am an American citizen. I'm allowed to say we horrendously underfunded our healthcare setup. What happened? Some higher up wanted to be able to track information about what was being going on the page. And so DoubleClick provides a nice, helpful get started guide, which includes fetching a JavaScript. So what happens is the code that constructs this URL is not living on the healthcare page. The code that constructs this JavaScript was another JavaScript GET request. So somewhere early on in the healthcare page, it says, include this JavaScript found on DoubleClick's page. It goes and grabs that JavaScript, comes back to this page. Then it uses that JavaScript, makes a request, and says, now grab information off the page, helpfully written by DoubleClick, and then it constructs this and sends it. All right. The point is that the information sent to trackers isn't just the visit. And the second point is that we are constructing URLs live. So everything that's being sent via URL is being constructed live on the web page by many sources. One of the tricks is put cookie content in the get string. So I said that only the main website can read the cookie. Fair enough, only the main website can use the cookie. So one thing I can do, so here the user ID is 47854. Goes to my bank. My bank constructs an index to HTML. In part of that construction, it creates a get string for DoubleClick that looks like user ID 47854. Wow, that looks similar. And this tracking ID. It's basically copying the cookie from one domain to another domain. So while cookies are isolated to the page that's being sent, with the assistance of that page, it is totally possible to copy that information over. This is sometimes called cookie syncing. And this is further used for tracking.
Why can't the browser use different tracking IDs every time?
The browser is not involved. This is JavaScript running on the browser. The browser is not constructing these IDs. So some long time in the past, the user visited their bank. When they visited their bank created this cookie, set it on their browser. Now, in the present, we go visit the bank. Now, you remember the whole, let's build a cute dog web page where things are being fetched? So what's happened is it now fetches the index file, and now it has to fetch all the content. Now, that index file is created by mybank.com. So when mybank.com creates all the URLs that needs to be fetched, it copies this user ID into the get string associated with DoubleClick. It creates that. It's being created in this example by my bank. So what my bank is doing is it is copying out a cookie information that was meant for only one domain to a different domain. This allows you to move a cookie between two different domains.
What's the role of DoubleClick?
A tracker. They're just purely a tracker. They track things. Marketing departments love them. They allow for targeted content. And so if you've ever bought a pair of shoes and suddenly every single advertisement on the entire internet is made of shoes, this is why. All right, the Verizon super cookie. I will get into, so I had previously listed something called topics on our schedule that was right before revision. I have now changed that to case studies. This is one of the two case studies I'll go into. So I'm going to go into it briefly here, but we'll talk about it in a lot more depth when we hit that lecture. The Verizon super cookie. This is a man-in-the-middle attack to inject a cookie into a web request from customers. So what happens, remember I said that cookies are sent, but they're actually sent separately from the main request. And they can be encrypted or not encrypted, optionally. So why can't I just add an unencrypted cookie? There's nothing stopping me from just sending a cookie to a server, is there? So this is a man-in-the-middle attack with an ISP. So the ISP saw a request come through, let's say to DoubleClick, because we're picking on DoubleClick today. So your browser is sending a message to DoubleClick. It knows that because it saw the DNS, because it knows the ISP number, because it knows a lot of things. And so it just adds a cookie onto the connection, potentially unencrypted. And that cookie is just simply sent to the server. And that cookie has an ID number. Verizon then took all of the information they have about which client they have, like their gender, age, all this information that Verizon happens to have because they're an ISP, and said, wow, you know, your server now has all these nice cookies that we created. If you give us some money, we'll tell you the mapping between that cookie information and the personally identifiable information of our client base. And this is known as the Verizon super cookie. The big two problems with this is, one, they never told users, and two, there's no way to protect against this. Honestly, there's literally nothing as a client you can do other than switch ISPs. Encryption will not protect you. It's possible a VPN would protect you, but man, that's a huge overhead to be paying against your own ISP. So this is a man-in-the-middle attack with cookies that enables tracking without you being involved. Okay, I think that's the end of cookies, and I have a couple slides on third-party malicious content before we move into real third-party malicious content. So I mentioned that we're building a web page. We build it off of a lot of sources. Sometimes those sources aren't so nice, particularly advertising. So I keep picking on advertising partially because I'm a privacy professional, but also because it's this really fascinating model. Everything else that's being loaded on your browser is being loaded because some developer thought this was a good idea. You might not agree with them, but they thought this was a good idea. They thought, you know, I need this package, or I really need to know where my visitors are going so I can better improve the situation. Or advertising is loaded because they want to make money, and they didn't pick who's going to do the advertising. So with advertising, you associate yourself with a conglomerate or an advertising network. AdMum, for example, or I forget all the different groups. There's one of them. You can grab one of them, and you insert code on your web page, and then somebody pays money to that advertising network, and the advertising network decides which ad will go on which pages in a live bidding scheme. And I'm not getting into that craziness. But the end result is that nobody knows what's going to show up on your page until about a microsecond before it lands there, because it is done via live bidding. This is an attack on the webmail site for Yahoo. Malicious payloads were being delivered to about 300,000 people per hour. The company guesses that about 9% of those, so 27,000 people per hour were being impacted. 27,000 people, that's a small town. They are infecting a small town per hour. That sounds terrifying. So how did this come about? They paid Yahoo. The attacker literally just paid Yahoo and handed them some malicious code and said, will you please put this in front of a bunch of users for us? All right, let's back up one level. This is weird numbers, isn't it? If I have 300,000 people per hour seeing this ad, why are only 27,000 people per hour being infected?
No.
Huh? 9%, which is roughly 27,000 people per hour. What's going on here? We saw before that you would get this information that Apache is doing. So I can see your exact browser version, and I can see your operating system version. What the latest operating system version is and what the latest browser version is public knowledge. So what happens is the site links to this server. I guess it should be a server. The advertising server. The advertising server has an if set in it. If version less than best, I don't know. Less than the most recent versions. Or in other words, if the version is vulnerable to a known attack vulnerability and it's clearly not been patched because the version number is too small, send to attack. If yes, send to nice ad. So the site you visited showed you an ad. If when your browser, because you're not visiting here, right? But your browser's visiting, isn't it? In order to construct this page, your browser has to visit the link. So your browser on your behalf sends a request off to the link, whatever that site is. Now, when it sends that request, it sends all the stuff we've been talking about. It sends your browser history, it sends your browser version, it sends your operating system version, it sends all the cookies. Then there's no reason that the first server contacted has to give you the content back, is there? No. They can happily just forward you to another server because that's how the internet works. So it runs a test on that information you sent it, and it either sends you to an attack server or a nice advertisement. which then sends the content back to your web page, which then your browser happily inserts inside your web page. So you are nicely on https mail.yahoo.com, and mail.yahoo.com is serving you malicious content, but only if you have an unpatched system. All right, is everyone still with me? Dangers of the internet. Now you're starting to understand why we spent so much time on blatantly obvious stuff yesterday, or Friday. And that's how you compromise 27,000 people per hour. This is also how you make sure mail.yahoo.com doesn't know you have a malicious ad. Because we patch our servers, don't we? The ones that are doing all the scanning, because we don't want to be compromised. And so scans of the ads ahead of time would have resulted in nice ad as opposed to malicious site.
So this data means that only 9% of the users have the latest version of.
No, opposite. Only 9% of the users have an old version.
Oh, yes. Old version, yes.
Yeah, so keep in mind this is an estimate. Third-party content can be used for tracking. We already kind of covered this, but let me state you something else that is obvious. This is an email. Have you ever seen a notification like this on the top of the email? To protect your privacy, Thunderbird has blocked remote content from in this message. You've probably seen that, even if you don't run Thunderbird, on other sites. Why is there remote content in my message? I know I've hidden it because this is a request from a student. Dear Dr. Vanier, please fix this problem I'm having. But this is 100% text. And it's an email from a student. So marketing emails, I totally buy why a marketing email might have an image. But why is an email from a student sending this alarm? All right, news to everybody. Emails are just HTML. Your email browser is a web browser. It renders HTML content. Everything we just talked about also happens off of your email because it is a web page. If you pull up the content of this web page, you get this. Did I highlight? No, I did not highlight. So if you read this, it's loading an image from Sidekick Open65, and it's got a display none, height of 1, width of 1, and I think somewhere in the long numbers it's got a color of white. This is called a web bug. This is a request to have my browser, aka my web client, my email client, fetch the image that's got no size to it. Why? Because this is a read receipt. It's telling whether or not I've opened the email. Because if I've opened the email, the image would load, and now the sender knows that I've opened the email. In this case, I chased the student up. It turns out they used to work for a marketing firm and still had some plugin installed, and that's how this had landed in a student email. This is very normal, though, to see off of marketing emails. So if you ever open up a marketing email, you'll notice if you skim down, suddenly every single URL has a different GID on it. And there's usually a bunch of images like this in it. Why? It's trying to figure out who opened the email for marketing purposes. All right, that took much longer than I thought. We are now going to switch slide decks over onto cross-site scripting. Odds are high that Friday we will also be doing cross-site scripting. There's a reason I hadn't done stuff yet. So, all right, that was cookies. But all of that was a nice lead into actual attacks, because up till now, I'm mostly just talking about privacy. People trying to track you in ways you don't want, but nothing like I'm talking about is really illegal, and it's mostly just them trying to fiddle with how the internet works to do stuff. A huge chunk of attacks on computer systems that involve taking in content from an end user fall into, my opinion, broadly this category. Data and code are different. Data should not be treated as code. Many attacks work because you're getting the computer to take in data and then treat it as code. This is what a buffer overflow does too, right? You take in some data, the data tries to overflow the buffer, and then get you to treat it as if it was code and start executing stuff you got from the end user. Do not execute stuff from end users. But a shocking percentage of problems happen because you get data in and you start treating it as code. And that happens a lot of times because data is passed back and forth. It's passed across trust boundaries. It's passed between like a server to the client. It's passed into the database. And at some point, we lose the fact that this was, at one point, given to us by a client and should not be treated this way. Cross-site scripting. This is probably one of the more famous ones. It falls into, broadly speaking, two types, persistent and non-persistent. Persistent just means that it's semi-permanent. So once the attack has been done, it stays on the web page unless somebody actively does something about it. Non-persistent only lacks the length of the attack, so it's very ethereal. It tends to just vanish. Let's start with persistent, because it's a bit easier to understand. What happens is the attacker visits a vulnerable website and sends the vulnerable website some malicious code. And I have a bunch of examples of how this looks later, but this is the high level. Attacker sends malicious code to the vulnerable website. Vulnerable website stores the code and gives it to the victim, who then executes it. Okay. Here is a trivial example. Imagine we have this guestbook. So I've got all the guestbook code just sitting over here. It's not particularly complicated. It's just got a web forum. It's got an input for your name, an input for the message, and a submit button. That's it. So what's going to happen is you can just type whatever you want in the box, you hit submit, and then it goes back to the server. Now, all the following attacks assume that the server is just happily taking this data in and then mimicking it back. So this website, once you hit submit, it happily takes you to the guest book. So the guest book, it says, your comments are greatly appreciated. Here's what everybody had to say. So Joe said, hi. John said, hello, badly spelled. How are you? Jane says, how does this guest book work? All right, this looks like, again, we're very simplistic code. You could add some stylization onto this, but the end result is just mimicking this out. How do we know what was originally data? And what's code? Because this is the life of HTML, isn't it? Because in HTML, this thing's a mess. There's a bunch of text here, and then there's this break. Where did the break come from? Makes that one worse. What if there was some JavaScript in there? The browser's just going to execute whatever the server gave it. So how did the server construct that page? Well, it probably has a database in the back end that contains name, message, probably date, but also name and message. It's got records of name and message. The request goes to the server constructs this page and delivers it to the browser. And it's constructing it by basically just concatenating a bunch of stuff that came from end users. So now everything here looks like it came from the server, but some of this originated from an end user. This allows us to do trivial attacks. So this is why we started with the post office. Trivial attacks, sadly to say, work. So for example, let's say that only logged in users can post to this guest book. So we assume that everyone that's posted to this guest book must be logged in because you can't get to this page without being logged in. What happens if the attacker does this? So Sam is logged in, and they say, hello, break. Bob : this is a terrible website. This results in this guest book. Is this evidence? Did Bob really say this is a terrible website? No. Okay, this is a trivial attack. This is the easy end. This isn't even scripting at this stage. But this is the basis that cross-site scripting is sitting on top of. This idea that you write one thing, you give it to the server writes it back. And if I were to look at the HTML sitting under this, this would look genuine. It would look like Bob had really written this. Obviously, it wouldn't look that way from the server's perspective if you went and dug into the server's code. But let's say I'm a lawyer and I'm screenshotting things. Bob totally said this horrible thing. All right, let's take this up a notch. JavaScript. How is JavaScript written on web pages? You just write script. some JavaScript, end of script tag. We have a mix of groups here, so not everywhere in here necessarily is good on web scripting, so we're slowing down in a couple places just to make sure everyone does know what I'm showing on the screen. But it just says hello, and then it's putting some JavaScript in there. So what does that do? Well, it causes the server to create the code on the left, where it happily goes along, and then there's a script alert, SQL injection, end of script. That is delivered to the browser as a full-up HTML file, and then the browser just starts executing all the code, producing this. All right. This wasn't very deep. This is an alert. I picked this predominantly because it was short, and I could easily write it on the slide. But hopefully I've just made the point that all of JavaScript is now open to you. And that's bad, because now what's happening is the attacker can post something on a website and have victims think that they are getting safe code from a website they trust, and you can execute arbitrary JavaScript code on someone else's computer. All right. If the attacker can execute JavaScript, then they can mess with the DOM. So for those of you who are not web programmers, the DOM stands for the Document Object Model. A website, which is not flat, is basically a hierarchy. I don't want to get too deep into website design, but the point is that each element on this is kind of built in this little tree. It's this nice hierarchy. It's called the DOM. JavaScript is designed to mess with the DOM. It does that because it wants to, say, move an object over here, make something appear, make something vanish, turn something red. And so in order to do that, it needs to be able to mess with that. If you're able to run arbitrary code on the web page, now that means that I can go and mess with the DOM, and I can alter anything the user is seeing. I can also grab stuff the user is seeing. So think back to the healthcare example. If I am entering data in a form, I can grab content the user has entered before they hit submit and send it to my backend server, because this is what JavaScript does. Here's just a whole list of things you can do with JavaScript on the left. One thing I can do is I can redirect the visitor somewhere else. So one of the things you can do with JavaScript is you can say, oh, you've just hit this page, sad, this is not the page you want. You should be on this other page. Now, we do this for a lot of reasons. Maybe we take down a page and we want to redirect visitors. There's a lot of reasons you might want to do a redirect. But this is done by just changing the document location via JavaScript. And if I can inject JavaScript, I can just send you to another page. So you think you just visited safe site, and your browser hopefully redirects you to evil site automatically. I can also create a web bug, that thing we were just talking about on email. So I can create a new image. I can set the source of the image to something I can generate myself. So I can literally say evil website, get me an image, run this stealing code to get the image for me. By the way, the cookie associated with the current website I am on is this. So I said that cookies are not able to be sent to another site by the computer. Yes, this is true. But if I am on goodsite.com, and goodsite.com has a cookie I know about, and I am JavaScript, I can fetch that cookie, I can append it to the end of a URL, and I can send it to evil site. The same way I do it with trackers. Another thing to do is create an iframe. I'm not going to get into this too deep, but there's just lots of things you can do. Okay, we're going to stop for think, pair, share here, because I want to settle the cross-site scripting into your brains and start really thinking about it. Particularly, this is a question I get usually at about this point. What prevents browsers from scanning for and blocking cross-site scripting attacks from happening? So why is the browser not protecting you against this? 1 minute, think about that. I was also showing you several examples where it was doing a call out. This, for example, is using 2 sites. But this is not cross-site scripting as much. But it's crossing over the site. All right. Non-persistent isn't very long, so I'm going to try to go through non-persistent quickly so that we can move to the next section cleanly on Friday. So non-persistent, the attack is sent directly from the attacker to the victim. So the attacker sends the victim some malicious, usually a malicious URL. The victim visits the URL, takes the get string, sends the get string to a cross-site vulnerable website. The cross-site vulnerable website then sends back the attack. Again, this is a situation in which you're basically sending something through a server to produce something that the browser now trusts, even if the original wasn't good. So we're going to use some really, and again, this is why we started with the post office, because I know most of the people in this room will look at me and go, this is stupid, Dr. Vanier. But this was news 2 weeks ago, by the way. A non-persistent attack, the attack does not persist past the attacker or victim session. The classic example is a search page. So if I put this URL in, and I say query equals computer security will show up on the screen. This means that I, as a potential attacker, have the ability to put content onto a Google page. I know you're all sitting thinking, Dr. Vanier, this is stupid. I know that text box is not coming. That's user content. But I want you to imagine your least technically knowledgeable relative. Victim clicks on this URL and gets a page that says whatever the attacker wants. Dogpile, for example. So in this example, it's in a search box. In this example, it's not in a search box, is it? It's just listed here on the page itself. One attack, note the date here, June 18th, 2025. So this is a fresh news report. What you do is you put the wrong phone number into a legit website. Here's the example. What did this look like? This is just a search. This is a search on Microsoft for the phrase, call us at phone number for free, which now appears at the top of the search results as call us at this phone number for free. Again, I want you to imagine your least technically knowledgeable relative and whether they might phone this number. So the way this attack works is I pay money to Google. Google helpfully puts up in the sponsored links at the top of the search, you're trying to find the free phone number for Microsoft. So they just search for, it shows if you type free software, a free phone number for Microsoft, it shows up in the sponsored search results that helpfully show above the normal search results for Google. You click on the link lands you on this page, which is a legit Microsoft page. And in nice big letters, it says the thing you want. And then you call the attacker. This is a non-persistent cross-site script. Low tech. But it gets the main point. These, just for fun, I tried to type into Dogpile because I noticed it was doing that, doing the alert thing, and it resulted in an error. So this can be defended server-side. We're talking almost entirely about how this functions, but a good server is scanning for this stuff. Basically, everything I just said from the prior one, you can kind of do here. So if you have the ability to, say, get Microsoft to redirect to you, so going back a few pages, I might give you a URL that legitimately goes to this location. But as soon as it gets to that location, it issues a redirect. So you might be looking at it in your email and go, oh, this really is a Microsoft page. You click on the real Microsoft page, it goes to the real Microsoft server, and then it goes through a redirect to the evil website. And if your eyes are not still up on that URL bar, which I can tell you most users are not, you are now on evil site even though you checked the URL. This is another example of a non-persistent cross-site attack. There's not a lot you can do about a cross-site attack as a user. The only things that really work are things like umatrix, things that block JavaScript, that make sure JavaScript don't run without you requesting it, that limits the number of places you're getting JavaScript code from. because a lot of times they don't put the JavaScript in the attack. They put a request to go fetch another file. That's usually run through JavaScript. But before you think that input sanitization is easy, there is a lot you can do to represent a character online. So there's a lot of languages in this world. It's, I know, shocking from a North American perspective, but it's not all English. And not everything works in ASCII letters. So in order to get a lot of other letters to even function, we have a whole messes of different ways to express letters. And if you make use of these, it can make pattern matching a nightmare. So the most basic example I showed you many slides back, in which there was a script, quote, plus, quote, ipt. So you can even just take script and separate it out. The browser will hopefully put it back together, but your searching code will have more trouble. More evil, I can use input sanitization for more complex input. So I can start with script. So I avoid using the word script. I can also URL encode characters. So this is a bunch of characters, and these are the URL encodings of those characters. So you have sometimes seen when there's a space. There's no space in your URL bar, are there? You see a space on the URL, but when you click it, you see, I think it's %20. Yeah, %20 up in the URL. What is %20? It's a space. Well, we can't have spaces in URLs, so we use %20. There is nothing stopping me from writing the entire script statement in this format. The computer will happily convert it back. So script alert, I could just write it that way. And my computer will still execute it because it's just a different way of format. JavaScript can also write text and push buttons. So you could, for example, go onto a social media site that is vulnerable, put in your content, and create a type of worm. So the idea is that I, as an attacker, write some script code, I post it onto a social media site. What does a social media site do? Shows it to other people. Their browsers execute it. Most of the sites have a box like this just kind of hanging out somewhere just in case you would like to post. Nothing is stopping your browser from taking code out of a cross-site scripting attack, copying it into the message, and hitting post. JavaScript can copy, JavaScript can read, and JavaScript can hit buttons. And now you have created a worm. And I will stop there, and Friday we will start in on cross-site request forgeries. And yeah. All right, thank you very much.